Spectroscopy, second page. I'm realizing yesterday I just talked about the kind of the concept of spectroscopy, where it came from. You know, burning materials in a flame and watching the flame color, and then getting more sophisticated over decades and centuries, and watching that film, that light. When we invented film, we got even better at that. We used film to capture those light bars so that we could look at them. And in that film, we could actually measure them. We could measure the distance between those light bars and make sense of them, begin to understand the composition of the materials that were being burned. So you're seeing a piece of something with sulfur in it. It's burning red, I think. You can smell the sulfur too. So you get a second hint, maybe the smell. Now, you didn't have the word sulfur back then. Maybe you had to invent a new word for that smell. You got to invent words in those days that didn't exist, instead of claiming words don't exist. So this staring at the campfire is still cool. So, all right, spectroscopy is the measurement of spectrums to gain information. There's an optical spectrum, which I've talked about. This is photons in the environment, as we call them, as we know them. Emissions from electrons moving around. So, yeah, there is a lot going on down there in that tiny world. So spectroscopy opened us up. It opened up the stars. We learned how to attach these instruments to telescopes and see more than the eye can see. So that's the some of the fascination and the amazing things that came out of this spectroscopy, this study of light. That really was the beginning of it. Now we've gone on, we do sound spectroscopy. You have instruments that measure, that amplify specific frequencies, right? An equalizer. Filters, so you can filter out a frequency. It is spectroscopy. It is signal analysis. It is signal discrimination. It is the studies of those that did the audio spectrum for us. So again, the spectroscopy word is wide until you begin to talk to what you're measuring, to what you are trying to understand. So in the light spectrum, who doesn't know a rainbow by any other name? We have all seen them. We know they exist, and now we understand why they exist. It's not some bunch of stars up in the heavens doing it directly. So we learned. And in this spectroscopy, we learned more and more about finite elements by studying the light emitted when we burn something. This is a type of destructive testing, because once you do this, whatever you're looking at has probably changed. It's another conversation. So there's two different testing types, destructive and non-destructive, in the industry anyway, both of which I've got some time with. So this spectroscopy part, this optical emission spectroscopy part, is old. It's older than our writing. That was the foundation of it, among many other things, these foundational principles that we have to use now to make our cell phones. So in this study of light, in the study of the sources of light, we made hard physical ties between properties, and then we went on to prove these ties and improve our understanding of the ties. We never got stupider. We've taken steps back, but it was usually with a few steps forward, and that seems to be changing due to politics. So, can we fix what we're doing? What do you mean by fix? Can we make it better? That's probably the goal. So spectroscopy is huge, huge science. I talked about optical emission spectroscopy, where you use seeing type devices. That's all we had in the beginning was our eyes to see with before we invented better detectors, better methodologies, deeper science, vacuum chambers, so that light doesn't have interference to worry about from a measurement standpoint, because you have to know the interference in your measurement to be able to either subtract it or just say there's too much, you can't make sense of the measurement. It's what we do because we learn. So this spectroscopy thing, again, big thingy, but in optical emissions, you start to address what you're talking about. If we're doing high particle emissions spectroscopy, it is different particles. It's not light that your eye can see. It's not photons that you're seeing. But you can't see these particles, so it takes detectors, and those detectors have very specific characteristics to do very specific things. The detectors in CERN are high energy particle detectors. They are studied down to the 50 decimal places now for accuracy to make sure they're doing what we think they're doing, and we're still not positive in some cases. So, all right, spectroscopy is a huge thing. The development of that science has gone on in multiple disciplines because it's used differently. An acoustic, an audio engineer is going to use sound. An optical engineer is going to use light. It might be the photographer that's trying to take a picture. He's going to have to know the properties of light and shadows and reflection and refraction and all those things, and yet he can still take beautiful pictures, right? So these things become unconscious. But there is math and equations behind a lot of the things that we can do. And some of these equations are ancient. They go back to China some thousands of years ago, and the industry and tools that they developed. It's fascinating what was going on in China at the same time as some other parts of the globe. So this spectroscopy thing is a common science. Everywhere you go, you might speak a different language, but if you speak spectroscopy, you have something in common to talk to, because it's science that you're talking to. And a lot of the terms and the words have common understanding and meaning. And I'm rambling on a bit here. So what's involved in this spectroscopy, this spectrum analysis? There's really two avenues here. You want to find the signal you're looking for. So you're looking for the color red, but all you can get is a brown. How do you get the color red from brown? That's a good question I don't have an answer to, but somebody does. So is the brown background that you can't get away from? You have to stop there because the brown paint can't be modified to make the red that you want? Probably. Probably. Because, well. So inside that math, there's noise. There's a signal to noise ratio that you have to understand in fine measurements. The signal is what you think is there, and the noise is what your instrument picks up from elsewhere. So can you subtract the noise and be able to see the signal with enough confidence to make a decision about it? This is the analytic software side of all of this. Inside of the analytic instruments are huge software engines doing fast Fourier transforms on waveforms to provide analysis information back into an engine that looks at input from the machine and reference libraries at its disposal. So it knows that when it sees those four bands or three major bands of light from a hydrogen atom, that it is a hydrogen atom. That those four bars among thousands of them from a fireplace means hydrogen. That is software analytics that goes into a whole nother domain. That would be the 501 level of this course for you. So, oh well, rambled too long. This one needed to be put together much better, maybe next year.